All right, so we'll get started now. My name's Adam Manzanares. I work for Samsung, and with me is Anissa. And what we're going to cover today is CXL ecosystem innovation, leveraging QEMU-based emulation. And I'll give the high-level intro, and then kind of give a little bit of background of what we do here, and then hand it over to Anissa to talk about the latest developments of what we're doing in this space. So, okay. So the first thing I want to cover is what is QEMU? So QEMU is an open source emulator and virtualizer. And let's unpack that a little bit, right? So I'll give some specific examples here, right? So starting from the bottom left here, one of the things that QEMU can do is full system emulation. So I'll put this in more practical terms. So if you're running, say, an x86-based CPU, and you're very interested in doing development for ARM platforms or RISC-V, you can actually emulate the full CPU from a different type of CPU. So you can be running on x86 and then run ARM system using QEMU. So that's one thing. It does full emulation of a CPU platform. The second thing that's very interesting too as well is if you don't want to go that far and you just want to have user mode emulation, so you can have a binary compiled for a different architecture and then actually run that binary on, say, x86 system running an ARM binary. You can just run it there. And lastly, the thing I'll talk about that it does very well, interfaces to something called KVM. And so KVM can be used as a hypervisor, and it becomes an open platform for doing virtualization. And it's near native performance, right? So it's hardware-based virtualization. It hooks into this, and is very useful for many different applications. And today we'll focus on the CXL part of it. So. So the last thing here, I think, what I want to talk about is why QEMU has been so useful for us at Samsung. And the main reason is that it helps us prototype end-to-end software for new hardware features, right? So I'm not as focused on purely the performance aspects here with QEMU. What we've really focused on is the interface. So, you may hear that we're in this era of hardware-software co-design, and really what that means is that there has to be an interface between the hardware and the operating system, and QEMU gives us the opportunity to build that interface through purely software-based mechanisms. And so, yeah, we use it for prototyping hardware features. And some clear examples over time, if you look over the history of where Samsung has been contributing to QEMU, we've been very active when ZNS was talked about, and then it transitions to FTP. And these are two technologies that focus on data placement within an SSD, was what they were. And lastly, what we'll talk about here, right? So we modeled our success story on the NVMe side, and we started developing CXL support in QEMU, and it was for us to implement features from the CXL standard, and then we implemented in QEMU, and then we did the host OS kernel software, and then that was our mechanism for kind of level setting with the industry, right? As we had the QEMU implementation, and we had the Linux kernel, and we would talk about, and so we'd have host software that leverages these features. And of course, we're doing this to support Samsung's hardware, right? So that's what the whole point of all of this is that we can be a little bit ahead of the hardware, just kind of proving out the interfaces. That way, when the hardware arrives in our hands, we have the software in place to go ahead and test our hardware. And what I would say is that the testing and validation has been some of our biggest success stories, right? Is that if we can get QEMU in people's hands and the hardware in people's hands and the corresponding software before like large-scale adoption, right? It allows us to build these testing teams, and they get knowledge of how to practically use these devices, and it helps us get the quick adoption of hardware. And one other bullet point that I think is good, and it's great that this is recorded, and we just were told of how we have a long tail on some of these discussions here, is that it brings other people into the ecosystem. So the team that we work on is called the Global Open Ecosystem Team, and our job is to make sure that people beyond Samsung know how to use our hardware well. And so that's one of the biggest, I would say, advantages of doing this thing in QEMU. It's not even our internal successes, but bringing other developers to work on these problems with us has been a huge win for us long term. So, all right. So then now the last part I'll hear, and I kind of touched in some of this, is that so CXL is a very interesting technology. Like me, myself, I think it's been like 3-4 years that I've been working on it and been involved in standards. And it's been one of the most enriching but frustrating experiences. And the reason is that I'm very fortunate to get access to early hardware, right? And CXL has required hardware from not only Samsung, but platform vendors. And so there is an ecosystem of hardware that has to be in place. And, you know, we're fortunate enough to have access to some of these things. But as I go outside and talk with people, I notice that not many people are in that same position. But if at least I can show them what we've done in QEMU, it gives them a good sense of where the industry may be headed. And so, you know, next-gen hardware access can be limited. And Anissa's, what she's focusing on, this DCD, is very relevant to memory sharing and memory pooling. And so, you know, it's a nice segue. Like, although we don't say AI in these slides, our work, that's the most interesting part of like where AI may change. They talk about KV caches and memory fabrics and this sort. And, you know, there's some proprietary ones, but also CXL may have a spot in there, right? And the specific work that Anissa's doing gives us a blueprint how to do that in a standardized way. And then, you know, again, we were very successful with NVMe. And then, you know, who are our main targets, right? I think we should give a little bit of time of where we've been very successful is that people working in operating systems development, you know, anybody doing driver development, and as well as some application prototyping. And Arun is going to have another session after this about where it's more of the application, but it lets people get ahead of the hardware in some ways, right, and prove out use cases. And lastly, another area that has been interesting is that we started in the operating system, and there was actually some pushback against how would we do management, like whether you'd have the BMC and how this would look and what a fabric manager is. You'll hear these talks within these terms in CXL. But QEMU gave us the opportunity to create these interfaces and show how the system software would interact for managing CXL devices as well. So we've had lots of wins in this space, and we continue to see more. And so now I will hand it off to Anissa.
Okay. So thank you, Adam. I'll briefly go over what features you can currently emulate, then go into more detail about dynamic capacity devices, what they are, and how memory is dynamically allocated from them, and then show a demo of how you can emulate it. So what can you currently emulate through QEMU? First, I want to make a disclaimer that some features may not be in upstream QEMU, especially some of the newer ones. The newest features are carried out of tree by the core maintainer of this module, Jonathan Cameron. So to access some of them, you may need to use a branch published to his personal GitLab. I would say that they match up for the most part, but I haven't done a side-by-side comparison, so I can't say exactly what is in upstream and what's not. But for the purposes of this demonstration, I'm going to be referencing Jonathan Cameron's branch. So to answer the question, right now, QEMU supports CXL memory devices and CXL switches. And within CXL memory devices, there are different subtypes, which include volatile or PMEM devices and dynamic capacity devices, and then more recently, some support for multi-headed single logical devices, or MHSLD, have been added. So that's just a single CXL device attached to multiple hosts for the purposes of what Adam just mentioned, memory pooling or even memory sharing. But for the rest of this presentation, I'll be focusing on dynamic capacity devices specifically. So in addition to what kind of devices you can emulate, there's also the question of how to talk to those devices in QEMU. There is support for both in-band and sideband communication. And to make that clearer, I'm going to go over this diagram for a more concrete example of a topology that you can emulate. So this diagram shows a simple topology with a CXL switch that has 3 downstream ports, each with a device attached. And T3 stands for type 3, which refers to CXL type 3 devices, and those are the memory expander types. So we have 3 CXL devices with memory resources attached to the switch. And we also have on the side over there a BMC, or baseboard management controller, which is a specialized controller that allows you to remotely monitor and manage your server components. And in this diagram, we can see that the host and the BMC talk to the switch through 2 separate endpoints. This separation is defined through something called a CCI, which stands for Component Command Interface. And the purpose of a CCI is to define which commands the device can receive and how the device is able to receive them. So in our example here, the switch implements two CCIs. One CCI defines what commands it can receive through the NCTP endpoint, which the BMC is connected to for sideband communication, and then the other defines what commands it can receive through the other endpoint, which the host goes through for in-band communication. And then earlier I mentioned that the focus of this presentation will be on dynamic capacity devices. So now that we have a better idea of how things fit together, I'll define what it is exactly and introduce the related concept of fabric management. So dynamic capacity devices are a subset of CXL memory devices that specifically allow you to add or release memory resources without resetting the device. And this process is facilitated by the fabric manager, or FM, and its main role is to dynamically configure the system's operational state using the FM API. And note that the FM is a logical process and not a hardware component, which means you can run it on the host, on a BMC like in the example here, on a CXL switch, or even as a state machine on the device itself. And I'll go over how the FM, the host, and the device interact in more detail in the next slide. But to quickly recap this slide before we move on, right now QEMU supports emulating CXL memory devices and CXL switches in both in-band and out-of-band communication. Okay. As promised, I'll talk more about how the fabric manager, host, and device interact. And specifically, I'm going to explain how memory is dynamically allocated. And this begins with the fabric manager, which sends the FM API add command to the device, telling it to make some extents available to the host. Then the device processes this information and records it into an event log and triggers an interrupt to the host. And the host gets notified, looks at the event log, and sees the extents that have been made available to it. It can choose to accept some, none, or all of the extents, and then the host will send its response to the device through another command. Then lastly, the device will physically back the accepted extents for that host, and the host can start using the added memory. And I wanted to go through this kind of simplified workflow first, but this actually doesn't show the full picture. So when we zoom out, there's a little bit more to it. And in the full picture, there's 5 different roles: the orchestrator, FM, device, host kernel, and the user. So we've just gone over the FM device and the host, but there's like a new thing here, which is the orchestrator. And at first glance, it may seem like it's doing kind of like the same thing as the FM based on what we just talked about, which is we see it's signaling to add capacity and remove capacity, which is similar to what the FM was doing in the previous diagram. But there is a subtle but important distinction that I'm going to clarify the difference in between the role of the manager versus the orchestrator. And so the orchestrator is actually the driver behind the whole process and decides when to add or release capacity. And the fabric manager is just the thing that encapsulates the FM API, which is how to tell the device whether to add or release the memory. But the fabric manager doesn't actually initiate anything on its own. So hopefully that difference is clear, and it should become more concrete in the demo video, which I will show later. But before that, I'm going to talk through the full flow of how memory is dynamically added in the context of this full workflow. So as we can see, the first step is create region, where the host user tells the kernel to create a region. So what is this region, and why do we need to do this? I want to clarify that this region is not to be confused with the device's regions. So the actual device can have multiple regions, but these device-side regions don't correspond to this region that we're talking about in the first step. The kernel region represents a chunk of physical addresses on the host side. So when you create a CXL memory region, you're really just telling the kernel how big of a range of new physical addresses to create. And then when you do this, it's important to note that this range is not actually backed by any resources on the device yet. But once you reserve that space, you can send the signal to add or release capacity, and that whole back and forth between the FM, the device, and the host happens. And then this region gets physically backed by resources on the device. But it is not necessarily fully backed by extent, meaning that this is a sparse region. So for example, you can create a 10 gigabyte region, but maybe you only add 5 gigabytes worth of extent, which makes it a sparse region because half of it is not actually backed by the device. And the kernel driver is the one that keeps track of how much is actually backed by the device. So then, how do you use that memory as the host user? This is where the DAX subsystem, or the DAX interface, comes into play. And this subsystem was originally introduced to expose persistent memory, which had different performance characteristics than traditional volatile memory. And it would expose the memory to applications because it would allow the memory to be handled separately from the general memory manager. So when you create a DAX device, the memory from the device is exposed through a file descriptor, and you can use mmap to map the memory to your process's virtual address space in DevDAX mode, or it can be reconfigured to system RAM mode and then added to the general memory pool. So the reason that the DAX subsystem is being reused to expose dynamic capacity is because but to PMEM, CXL memory has different performance characteristics than traditional volatile memory. It can be persistent or volatile, but the mechanism to handle this kind of special memory already exists in the DAX subsystem. And so, like I said, there are 2 ways to use a DAX device. The first method is to use it in DevDAX mode, and where the device is exposed through a file descriptor, and you can use mmap to map it to your process's address space. And then when you're done, you can unmap it and then release the DAX device and release the extents backing it. So the second option is to reconfigure it to system RAM mode. And when you do this, the memory gets added to the general memory pool, and the option to do this was previously added when the use case for PMEM expanded to using it as more memory, regardless of its special characteristics. So you can add memory backed by a DCD to the general memory pool, but that makes releasing it more complicated than keeping it as a DAX device. And I mean, to be 100% clear, this whole flow only applies to dynamic capacity devices and not regular CXL memory devices. So to quickly recap this slide, in order to use dynamically added memory, first we need to tell the kernel to reserve a new range through the create region command, and then we can add and release extents to back that region, and then the memory gets exposed through the DAX device, and there are multiple ways to use that DAX device. So the reason I'm coming back to the roles is because this is all building up to the demo video I will show you, where we emulate all of these roles and the behavior shown here. And we can emulate a dynamic capacity device and all the buses and whatnot, connecting it to the host using QEMU, which is all about that physical layer. But I emphasized earlier that the fabric manager is a logical construct that acts as a wrapper for the FM API. So the FM needs to send the FM API add command to the device so it knows to make space for the host. And this is still like a missing piece of the puzzle before we can emulate the device, the host, and the buses that connect them. And we still need something to send the FM API add command to the device. And that leads me to my next slide. So this is where we see the need for libcxlmi, which stands for CXL Management Interface Library. This is a user space library that allows you to send any command to any CXL device. And for those of you storage folks who are familiar with libnvme, which is the basis of NVMe CLI, This is the equivalent for CXL devices. So, libnvme and NVMe CLI have both proven extremely useful in industry to manage NVMe devices, which is why we see a similar need for a library to do the same for CXL devices. libnvme is more mature, which is to be expected, considering CXL is still an emerging technology. But the goal remains the same, and we need a library to interact with and manage the device. So just to reiterate, libcxlmi is a user space library that allows you to send any command to any CXL device without being bound to some specific implementation, such as the kernel driver, which can limit which commands get sent to the primary mailbox. And in that way, it is similar to what libnvme does for NVMe devices. We can use this library to send FM API commands to the device, and then I'll be using it in the demo video. So now that we know how it all works, let me go over the configuration of what we'll be emulating, and then I'll show the demo video. So we'll emulate a very basic topology with one DCD directly attached to the host. And just like we talked about before, the device implements two CCIs, which basically means you can communicate with the device in two different ways. And the host talks to the device through its mailbox CCI, so it'll send a message to the device's mailbox registers. And then we'll also emulate an MCTP-enabled bus for sideband communication between the host and the device. MCTP is a management protocol, so the underlying physical bus can be anything that supports the protocol, such as I2C, USB, or PCIe VDM. And this brings me back to what I said earlier about libcxlmi not being tied to a specific interface, because it doesn't care what you have underneath physically. All it needs to do is send MCTP messages through whatever bus you have. So therefore, libcxlmi will run on the host in this configuration, acting as the fabric manager. And this is a little different from the first example of the topology I showed, where the fabric manager was run on a BMC. But if you remember, the fabric manager is a logical process and can be run on either. So to make things simpler, we'll just clone libcxlmi on the host and use it as the FM instead of adding more complexity by emulating a whole BMC. So this brings me back to another point, that emulating all the hardware details is not exactly necessary to develop the software that should be able to run on many different configurations. And in the demo, I'll use an example program from libcxlmi that prompts the user to interactively add or release extents in the terminal. So in this case, us, the user, we will be the orchestrator. And if we combine everything that we talked about so far, we, the user, will be acting as the orchestrator and use libcxlmi, the fabric manager, to send FM API commands to the device. The host will process the command and tell the host, the device will process the command and tell the host, and the host will see the extents that have been made available to it and send its response back to the device. Finally, the device will allocate those extents to the host, physically backing that memory. And then the host will be able to start using that memory either as a DAX device or reconfiguring the DAX device to be used as general system RAM. So now I'll actually show you how to do all this in the demo video. And in this demo, I'll be using a tool called CXL Test Tool to automate some of the setup and scripting. And this tool is openly available, and I have a link to it in the next slide. Let me play. Okay. So this first command is just going to start a VM with the topology that we just went over. Pause. Okay. And then I need to load some of the necessary kernel modules. Can you guys see this? Okay.
Don't worry, take a look later.
Okay, sure. Sorry. So I'll need to load some of the kernel modules, and this one takes a while because it's loading all the modules in the VM that we just started. And then next, I need to enable the MCTP endpoints. And as you can see, this tool kind of just wraps up a bunch of scripts I want to run for setting up the right environment. And the mouse. Where's the mouse? Okay. Next, I'm going to log into the VM. And using the CXL list command, we can verify that the CXL topology looks correct. And we see that we should see, well, I guess you can't really see, but there's a CXL device called MEM0. Hold on. So there's a CXL device called MEM0, which checks out because we emulated one dynamic capacity device. And then next, we'll need to create the region that's the create region step that I just talked about earlier. In order to add memory dynamically, we need to create a region so the kernel knows how big of a range of new physical addresses to create. And we can check that the region was created properly using the CXL list command again. And right here, it shows that we've created region 0. And then before we actually add any memory, I'm going to run the lsmem command to show how much memory we have right now. And it's hard to see, but we have 8 gigs of RAM right now. And then we'll use the libcxlmi example program I just talked about to interactively add or release extents. So I'm just going to compile the library first. There's the interactive program. And then I first print the extents that we currently have, which is 0. And why is it doing that? Sorry. And then I'm going to just add a single extent with 512 megabytes. And then when I print it, we see that we have a new extent allocated for us. And when we exit, the program will help us create a DAX device from the extent that we just added. So this command is we'll create a DAX device from region 0, which is the region that we created earlier with the create region command. And then DAXCTL list is going to show us and verify that the DAX device was, actually created correctly. And then when we do the lsmem command again, it will show us that we have an extra 512 megabytes of RAM that we just added. Sorry, that was hard to see. Okay, next slide. And so to wrap things up, I've included a few links to resources that may be useful for referencing later. So first, I have a link to some documentation on how to recreate the demo that I just showed you. And as you just saw in the demo video, I used a CXL test tool program to do a lot of the setup steps and automate, starting up the VM and loading the kernel modules. But because I wanted to keep the number of extra dependencies you need to a minimum, the guide just has the raw commands and the scripts. So the steps in this guide are going to be a little bit different than you might see in the video, but CXL Test Tool basically just packages those scripts that you would run into a single command, but beneath it all, it's all the same thing. I've also included a link to CXL Test Tool, which is extremely useful if you are wanting to do more development in this area, with helping you set up your environment correctly and easily managing and starting VMs with different topologies. It includes a set of pre-configured topologies that you can use and a number of scripts to help you do things such as, if you remember from the demo, configuring the MCTP endpoints and helping you load the right modules. So I've also included a link to some kernel documentation pages that go over what I talked about in the presentation in more depth, but also other topics that you may be interested in, such as platform configuration and what happens during boot, and et cetera. And so the last link here is a link to libcxlmi, which is a CXL device management library used as the FM in the demo. And to quickly recap some of the main points from today, we went over why emulation is valuable in the context of CXL, what you can currently emulate in QEMU, how memory is added from a dynamic capacity device, including the interaction between the orchestrator, fabric manager, device, host kernel, and the user application. So that whole end-to-end pipeline. And we also talked about how to emulate that, and I've linked some tools and libraries that are available to help. And lastly, I want to thank everyone on this page here. They all have contributed greatly to the CXL software ecosystem in QEMU, the kernel driver, and all the other tools and libraries that are needed. So without them, the demo would not have been possible. And so thank you to all these people. And thank you for coming to this session. Questions? Yes?
So in your demo, you're acting as the orchestrator, right?
Yes.
The command you're typing in is you're acting as the orchestrator.
Yeah. So the interactive program will ask you, it was hard to see, sorry, but the program will ask you, do you want to add or release an extent? So then we, the user, will enter I want to add an extent. So we're making the decision about when to add something and how much to add or release. So that would make us the orchestrator. Yeah. Yes?
The orchestrator tracks allocated memory.
Don't forget to repeat the question.
Oh, sorry. So the question was, does the orchestrator track the allocated memory? So are you referring to what I said when the region in the kernel was sparse and it might not be fully backed by physical resources on the device? Okay, so that would be the kernel driver. In the driver, it has a sparse region data structure that keeps track of what host physical addresses are actually backed by device physical addresses.
So I have a question along the same lines, right? I think probably in the example that you're talking about, you only allow one host in your, yes, so there's no external NFU for to be able to handle, because it would be an issue if you actually did have multi-tenant access at the same time. Okay.
Should I repeat?
This is just a guess on my part.
Anissa's asking me for help here. So we kind of alluded to this. So when we started working on these slides and looking at DCD, we personally emulate an FM being a separate host, and we have different ways. Like there's a USB interface. There's multiple ways of doing this, and we've looked at different ways of doing this to try to accurately model what would actually happen in systems. For us, the fact that you have two separate systems could be managed by a device knowing how much capacity was given to two hosts, say. So I'll be more specific. We are looking at memory pooling using this basic mechanism. So DCD itself allows you to add or remove the memory from a single host, but if you look at the existing QEMU code, the most recent one, they have what's called the multi-headed single logical device. And here you can actually, we're going to have a demo soon, like we'll have a blog post about this, where you have two QEMU instances get launched on the same host. The first one, you have this multi-headed device and you initialize it, and then the second host that you set up, you point it back to that first one. And there's some shared memory of the data structure that represents the memory given to the host, right? Like from a control plane perspective. So from a control plane perspective, we actually can do pooling and show that DCD can be used to move the memory from one host to another. At least like adding from one host, removing from that first host, and then moving the memory over to a second host, right? You know, what you can do beyond that, you kind of can dream up on your own, right? Like, but the basic mechanisms and basic infrastructure is there, and we really want people to realize that, right? Like, I'm involved in OCP CMS, and that forum is very difficult to talk about memory sharing and memory pooling because, you know, we're talking about things a little further out, right? And so to me, this is a nice concrete mechanism where we can show memory pooled between two hosts. And yes, it is a simple example, but it shows that the standard and the host software is ready. Right, it's here and it's ready, and you can use it, and so that's kind of what I'm telling everyone. And you know, I'll leverage this time. Sorry to take away from everyone, but I really want to push for CXL.io as control plane. Right, so that's one of the things I'm getting up here is I know people are worried about CXL.mem and who has the highest bandwidth and all these different discussions come up, but in my opinion, I would be a little bit frustrated if someone came and said, we need a new control plane for your memory interconnect, right?
Yeah, I think the separate point that comes up out of this question is that if you have multi-tenancy, you need an MMU of some sort, and in this case, you're actually using the first host as the MMU.
I disagree with that. So like the question is, do you need like memory management across two hosts? Right, I think is more of the question, right? Is what you're thinking?
If you have a shared memory source, the answer is absolutely.
I don't think so. So I think there's hints of this. So one work I would point to that hints in this direction is FAMFS, right, from Micron, right? And the interesting thing about this is that you could imagine shared memory from two separate OSs that are really not aware of each other, right? But the fact that the memory is shared, you could peek at the memory or make some assumptions of how the memory is used to allow coordination between two hosts. But you don't have the two hosts sharing like one OS instance, right? The memory itself and how you use it dictates what's allowable. Yes, it's complicated, but I think take a look at this.
Without dragging this entire thing down, you're talking about shared memory, which would be memory that both hosts can actually see.
At the same time, yes.
At the same time, as opposed to co-located memory, which would be multiple hosts coming in and allocating memory out of the same pool, but not necessarily sharing that memory.
Yes, so there's two separate problems we're talking about here. One is access to a single device that provides memory to multiple hosts. That's the memory pooling example that I think of. Then there's also memory sharing. But in my mind, like, okay, let's take a step back. The orchestrator in these examples is the one that would own all the memory pooling decisions for all the hosts. You could run this software from one central location, and the analogy I would give is think of distributed storage systems, right? Is that typically for your metadata, you have a single entity in charge of this, or, you know, it might be replicated, you know, X, Y, and Z, but the memory side is very similar, right, is that this orchestrator is going to have to know the state of the system. And, I'm at a device company, right? But we know pretty well, like an approximation of what our end users do, right? And they're already managing these things, right? You got to place which VM runs on which system, right? They already have a pretty global picture of all the systems in there. And so I don't think they're much further from looking at a device that provides memory to multiple hosts, at least in my opinion, at least from orchestrating at a higher level. I think it's already being done. Okay. Yeah.
Plus, I'm in HPC. So
Okay.
we're going to pre-schedule everything.
Okay.
So we're going to run a scheduler like Slurm or whatever. We have our own livermore called Flux.
Okay.
That can apply multi-constraint scheduling. We would constrain it and say, in order to launch this job, you must have this much memory available. And then allocate it through what you're talking about, and then start the job.
Okay.
The memory like mounted on there prologue scripts.
This is officially after session discussion, because they're only capturing one side of this.
Yes. Oh, yeah. So maybe repeat, right? So audience member from the HPC community mentioned that HPC schedulers take the resources available, right? And so you describe your job. I actually came from HPC, but and so what they could do is potentially assign resources per job while the job is running, and like assign memory from one device to multiple hosts or whatever host it needs to, and then tear it down once the job is over too, as well. So. Yeah.
In order to do that, you need telemetry to know the state for failures, for example. So if the memory drops. So I wasn't sure, would I query that? Query it during the job, or if the memory fails during the job. I kind of need to track that memory so I don't go assigning it to the next job.
And then the follow-up was, as the job may be running, what is the telemetry available to go and query? I've spent way less on that. My thought process generally is that once we allocate it, it stays up. But that's a good point that at this moment, at least us initially, have stayed away a little bit from, right? Like we're just more on that initial blueprint. But I think, as adoption increases or as we start talking more and we get them in the field, that kind of level of management is always the next thing that we have. And it happens with NVMe SSDs as well, too. So, yeah. Okay. Any other questions? All right. Okay. Thank you.
Thank you.